Before we do the next two examples, I'm just going to refresh your memory on what we're doing when we're working with the nature of roots and the sort of language that we need to look for in the questions where we can actually have that moment and know that, oh, okay, so we are looking at the nature of roots. The nature of roots just wants us to look at what are the roots like. First of all, we need to know what they're talking about when they're talking about the roots. So the roots refer to your x solutions. Your x solutions. So if you think about a quadratic equation that is in this form, right? Something like that, where a and b and c just takes on certain values. If we solve this, blah, 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 we solve this and we get to a point, okay, x is equal to 2 or x is equal to -3 or whatever, something like that. Those would be the roots. Those are the x solution that satisfies the equation. We can also go and represent that as a parabola. So something like that might look like that, where we say, okay, we've got an x-intercept of -3 and by 2, and the parabola, when we draw it, it would be something like that. So note that this parabola over there, it has two intercepts, two distinct, different intercepts. So the nature of those roots are that they are real, they exist, and they are distinct, they are different. So what else can we come across with the nature of roots? Well, where we're not able to solve it, where you can't find the factors for it when you factorize, or when your calculator gives you weird eye for imaginary or complex numbers. In that case, it's when we're dealing with something like this, where you have a parabola like that. There are no real solutions. There's no roots. It never cuts the x-axis. So a description for that will be no real solutions. We can't get to that point of solving for x for that equation. And then visually we represent it like I just drew there. What else can we come across? Well, we can come across an example where if you draw a parabola where there's just one root because they share that root. Like when your turning point is on there, and let's say your root over there, whatever it is, -2. So it's one root because they share it. It's repeat. It's when you solve your quadratic equations, it's when you get to something like that. It is the same root. So that would look something like that. Okay, now let's put all of this together. So when we think about nature of roots, we're not going to go so far as we just did to solve for x. We're not going to get to this point of getting to x is this or x is that. We just want the nature, a prediction of what the root will look like. And that's where delta comes in, or our discriminant, whatever you call it. Our delta is equal to b squared minus 4ac. Where do we get that from? Where do we recognize that from? If you think about your quadratic formula that we use to solve for x, it looks like this, right? There's our quadratic formula. There is our discriminant. There is our delta, whatever you call it. I'm going to call it delta from now on. All right. Now, why do we use that as our tool that will tell us what will the roots be like? Because it is under a square root. What happens underneath that square root determines what the roots will be like. Because remember, underneath the square root, we don't want the square root of a negative number. That will give us non-real numbers. Your calculator would give you something funny. So when you land up with a negative underneath the square root, there will be no real solutions. We can't find that. So there's the first thing. When your delta is smaller than 0, it means basically that you land up with a negative underneath the square root, and then it means that the roots will be non-real. Non-real roots. That's our prediction what it will be like. Do we know exactly what the roots? Well, they're non-real roots. Visual is that one over there, where it never cuts the x-axis. Okay, then what else? Well, if my delta is equal to 0, let's see what will happen then. Well, think about it. Underneath, let's say you've got x is equal to -2 plus minus. Underneath the square root is a 0 when delta is equal to 0 over, say, 4 or whatever. We're going to land up with one root. because we've got negative 2 plus or minus the square root of 0. We've just got 0 there over 4. So we've got negative 2 plus 0 or negative 2 minus 0. We are going to land up with the exact same root twice. So when our delta is equal to 0, we will have a root. There will be a real root, real equal root. Trying to think if I said that the best possible way. Yeah, it's real and it's an equal root. Visual for that, when we've got a turning point and it shares that root. You get the picture there. Then, what happens when our delta is bigger than 0? Well, if we've got underneath the square root a number that is bigger than 0, so let's say, for example, we get positive 16, well, that will give us a 4. We can simplify that. We can get the square root of that. It will give us 4. So that will mean that we will have real and distinct or different roots. So real and, let me just say real roots for now. We're going to make a distinction there quickly. I'm using that word distinct a lot. So let's just quickly see. When your delta is bigger than 0, we've got real roots. We've got real root. But now we can take it one step further. If your delta is bigger than 0 and underneath the square root, you've got a perfect square. So in other words, your delta is a perfect square. Let me write that better. So if your delta is bigger than 0 and a perfect square, what do I mean by a perfect square? Square root of 16, square root of 25. You can get the square root of it without your calculator, if you know your perfect squares, of course. Then your roots will be real and your roots will be rational. Rational, because if we get the square root of 16, it will give us 4. If we get the square root of 25, it will give us 5. So we're never going to be confronted with some decimal irrational numbers. When will we? Well, when your delta is bigger than 0 and underneath your square root, you've got a non-perfect square. What will the roots be then? A non-perfect square, what will be an example of that? A non-perfect square will be a square root of 17. It's not a perfect square. So that will be an irrational number. When you put it into a calculator, it would give you like 4, what? Okay. So then the roots will be real. They exist, but they will be irrational. Okay. Let's just wrap it up. There's our delta. There is, if we work out delta based on whether delta is bigger than 0, equal to 0, or smaller than 0, we would be able to predict and say the roots will be non-real or real, or there will only be one root. But then we can make a further distinction when the roots are bigger than 0. If the roots are bigger than 0 and it is a perfect square, then the roots will be rational. If our delta is bigger than 0 and underneath the square root, so our delta is a non-perfect square, then the roots will be irrational. It's a lot, but it makes sense, doesn't it? Let's look at 2 examples. Discuss the nature of roots. So they're telling us very clearly what we're supposed to do. They can change the language slightly and say, discuss what the roots are like. And you must be able to pick up that we're dealing with nature of roots. So discuss the nature of roots for the following equation. Now, note, you cannot go and solve for x and get to the point where you say x is this or x is that, and then you say, oh, look, they are real. They're not saying solve for x. We're just going to discuss the nature of roots. What are we predicting will the roots be like? Okay, so always make sure that you have this in standard form. It is in standard form at the moment, where we can easily identify our a as 2, our b as 5, and our c as -1. So let's go work out our delta so that we can comment on the nature of these roots. B squared minus 4ac. So delta would be equal to b squared is 5 squared minus 4. A is 2, c is negative 1. So that would be 25. And that will give us, I think it's plus 8. Yeah. So delta is equal to 33. Okay, now let's use that to comment on the nature of roots. Well, delta is definitely bigger than 0 because 33 is bigger than 0. Therefore, the roots will be real. But 33 is also a non-perfect square. We cannot get the square root of 33 without our calculators. It is irrational. So that means the roots will be real and it will also be irrational. And we also need to put in there, maybe let me just do that better. The roots will be real. They will be different or distinct, meaning that the roots will be two separate things. The one will be x is equal to minus 2.3 and the other one is plus 5.1 or whatever. So they are real, they exist. They are different, so they are distinct. And then they will also be irrational. And there we said everything we possibly can about the nature of the roots of that equation. If you were to go ahead now and you go and solve for x, where you do all the work, blah, 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 and you solve for x and you get to x is equal to something, then it will prove what we just said over here. You will get to roots that are real, you will get to roots that are different, and they will be irrational. Next up. There's a third example for this under the challenge section of equations because they like bringing in some problem solving with this. Let's read. It is given, so we are given that the roots of this equation are real. Find m. So this is different. We're not just going to discuss the roots, they are telling us the roots are real. They're telling us that. And we need to find that m. What do we know when the roots are real? So they are giving us that our delta is bigger or equal to 0. Why am I also make it equal to 0? Because if the roots are the same thing, remember, if delta is equal to 0, it means that there will be one root, but it's still real. So if they are telling us that our roots are real, it means that our delta is bigger or equal to 0. So we can use that. Okay, then we need to find that m. Where does that m come in? We have to go write this in standard form. So I'm going to take this and I'm going to go put it into standard form that we can identify our a, our b, and our c. I get x squared plus 2x. Then I'm bringing that m over is equal to 0. This is an important part to identify your a and your b and your c correctly. Our a value is just 1, right? Our b value is our coefficient to our x there, which is 2. And our c value is our constant term that does not have an x in the term, right? So that is negative m. Because m is what we're trying to solve. So be okay with having m in there. Okay. We know that delta must be bigger or equal to 0. So now I'm going to go replace my delta. Well, I know that delta is equal to b squared minus 4ac, which is bigger or equal to 0. Setting it up like this with inequality is key, I found. So b squared, 2 squared minus 4a times c. And all of that will be bigger or equal to 0. Let's simplify. 4, when I multiply all of that out, it will give me plus 4m. And that will be bigger or equal to 0. An inequality, a linear inequality that we need to solve. So 4m will be bigger or equal to, take that one over. And now I'm going to divide both sides by 4. Let me just carry on over there. If I divide both sides by 4, I'm going to land up with m is bigger or equal to negative 4 divided by 4 is negative 1. And that's it. Let's just talk about what we just found. we found a whole range of answers. M can either be equal to -1, or if M is bigger than -1, M can be 0, 1, 2, 3, 3.5, 4.25, whatever. Anything that is bigger than -1. And if we put that into that equation, the roots will be real. So if we have x squared plus 2x, and anything that is bigger than 1, so let's choose 10, and we make M 10, if we work that out, the roots will be real. So M can be a ton of values, anything that's bigger than -1. When we plug it in, the roots for that equation will be real. All right. If you're up for a challenge for nature of roots, head over to the challenge section, and otherwise carry on to the next video. Try some of these on your own. It's not as bad as it seems. You just read carefully, give it a go. You'll find a copy of these 2 examples in the worksheet as well, and I'll just put a link in the description for that.